Hello, everyone. My name is Sasha, and I'm here with my colleagues Amayrani and Jun. Today, we'll be presenting our ELT pipeline for ADS 507 with Professor Dylan Orr. Our project focuses on processing real time travel data from the Washington State Department of Transportation. We built our pipeline using MySQL for data storage, Python for automation, and SQL for transformations, all while leveraging Github for collaboration. This automated pipeline efficiently ingests, transforms, and stores data, creating a structured dataset for analysis and decision making.
Hi, my name is Amayrani and I will explain the problem our project aims to solve. Every day, drivers face unpredictable delays due to traffic congestions, accidents, and severe weather conditions. It is difficult to make safe and efficient travel decisions without real-time insights. One major issue is that traffic data is scattered across multiple sources, making it hard to track incidents efficiently. On top of that, there's no automated system to combine and analyze this information in one place. Lastly, inconsistent formats and missing values make it challenging to detect patterns and predict traffic conditions accurately. To address these issues, we built a structured automated data pipeline that consolidates WSDOT travel alerts, cleans inconsistencies, and ensures real-time insights for better decision making.
Hi, my name is Jun, and I'd like to walk you through our system architecture. Our pipeline follows an ELT, or an extract, load, and transform approach to efficiently process real time traffic data from the Washington State Department of Transportation. First, in the extract phase, we retrieve JSON data from Washington State's DOT's public RESTful APIs using API keys for authentication. A Python script scheduled to run every 4 hours using a cron job fetches and processes this data automatically. Next, in the load phase, the raw data is stored in a MySQL database on Azure, ensuring structured storage, security, and scalability. Finally, during transformation, we use SQL queries to clean, normalize, and structure the data into dimension tables. This makes it optimized for efficient analysis and integration with visualization tools like Tableau.
Now that we've covered our architecture, let's take a look at how we transform the data. Once raw data is stored in MySQL, we apply a series of stored procedures to transform it into a structured format. Each stored procedure automatically triggers when new data is ingested, ensuring real time updates. Transform travel time extracts key metrics like average travel time, current time, and distance. It also parses start and end locations, generates hashed location keys, and maps road names using a lookup table. Additionally, Unix timestamps are converted to readable datetime formats, and a refresh timestamp is added for tracking updates. Final results are stored in the time travel dim table. Transform weather alerts structures weather condition data, including temperature, humidity, precipitation, wind speed, and visibility. It also parses geospatial data, extracts road names using a regex pattern, and maps milepost values when available. Missing values are handled by replacing them with unknown, and timestamps are converted for better readability. Final results are stored in the weather alerts dim table. Lastly, transform traffic alerts normalizes the traffic alert data, extracting details like event category, status, priority, and description. It also parses start and end locations, creates hash location keys, and ensures road names are standardized. Like our travel time data, timestamps are converted and a refresh timestamp is added to track updates. Final results are stored in the traffic alerts dim table. By structuring the data into dimension tables, we enable fast, efficient querying and visualization.
Now that we've seen how our system processes data, let's explore how it benefits users. Our automated data pipeline consolidates real-time traffic, weather, and road alerts, cleans and structures messy data for improved accuracy, stores insight in MySQL for easy access, powers an interactive Tableau dashboard for decision making. This solution streamlines access to critical travel data, helping drivers, city planners, and emergency responders make faster, smarter decisions.
To ensure pipeline reliability, we've implemented three key monitoring systems. First, API fetch logs confirm whether the latest API call was successful ensuring that we are retrieving data as expected. Next, API fetch history stores past API responses, including timestamps and HTTP response codes. This allows us to monitor trends over time and quickly identify potential issues with data retrieval. Finally, application logs track ELT execution, capturing timestamps, log levels, and transformation steps. These logs help with debugging, performance monitoring, and ensuring a smooth data pipeline. By integrating these monitoring systems, we improve traceability, detect failures early, and maintain a reliable data processing workflow.
As part of this project, we created a comprehensive design document that has 7 sections. The first is Home, which gives an overview of the project, important links, future recommendations, and general access instructions. Next, the Data Dictionary provides basic table information, including details on column names, explanations, and data types within the MySQL database. Dashboard acts as a user guide for the Tableau. It outlines key filters and general user information. The EER diagram is a visual representation of the MySQL database. The ELT process is our architectural diagram of the extract, load, and transform process. Additionally, the document links to the source diagram and lucid chart for closer inspection. Monitoring covers how we track the pipeline performance and potential ELT failures. Code review documents our peer review process throughout the project. With this structured documentation, our pipeline is well documented, reproducible, and scalable for future improvements.
Deploying our traffic data pipeline involves 4 key steps for smooth data processing and monitoring. First, we set up the environment by installing dependencies using Conda or a virtual environment. Next, we configure the database and APIs, securely storing credentials in a .env file for protected access. Then, we automate ELT execution with a cron job running every 4 hours, adjustable as needed. Finally, we monitor performance using logs to track execution, detect failures, and ensure reliable data flow. For full deployment details, check out our GitHub repository.
As we built this system, we ran into a few key challenges. One of them was deploying dashboards due to restrictions in Tableau. There was no automated monitoring, which meant we had to manually check system performance. Whenever the API data changed, we had to update everything manually, making the process inefficient. Security was another concern, as we had missing encryption and weak access controls. Database inefficiency slowed down queries, which affected performance. And finally, scalability can be an issue with growing data. Through these challenges, we learned a lot. First, we realized how important it is to optimize API calls for better efficiencies and performance. We also saw the value of clean, well-structured data in making analysis more effective. We learned that integrating multiple data sources smoothly is crucial for a system that runs well, and most importantly, we recognize that security needs to be a bigger priority in future versions. With these lessons in mind, here are some improvements that can be implemented. Automating alerts will allow real-time monitoring instead of relying on manual checks. Expanding storage capacity will help manage the growing volume of data. Enhancing weather insights will provide better and more actionable analysis. And finally, strengthening security by adding encryption and stricter access controls will help protect the system from potential threats. These improvements will create a more efficient, scalable, and secure system, ensuring it can handle future challenges effectively.